we still actually have just a little bit that we need to finish up in 3.4 because I wanted to do another difference quotient. And then there was one on the homework that we didn't have a chance to do an example of during class yesterday, so I want to go over an example like that, where it gives you function notation with two different outputs, and then it asks you to find the equation of that function. So we'll do an example like that. So on my difference quotient, I'm going to try to break it down and go a little bit slower than I did yesterday through this so that hopefully all the pieces make sense. So we are going to be subtracting these two things up in our numerator. So let's talk about what f of x plus h is going to look like. So I'm coming over here. This is the function rule they've given me to work with. So in that function rule, in the place of the x, I'm putting x plus h. So I need to simplify that. We're going to square this binomial. What does it look like when I square that binomial? Yes. X squared plus 2xh plus h squared. I brought down my other pieces. I'm going to distribute the 3 to each piece. So I have 3x squared plus 6xh plus 3h squared plus 2, because he just gets to come down. This is f of x plus h. So this right here goes first in my numerator. So here's this big difference quotient that we have. This goes first. And then we're going to be subtracting what? Yes. This right here is what I am subtracting, because that is my f of x. All over h, because I can't leave this guy out right here. You guys understand a little bit better where I'm getting all of these pieces from? Right, Lainey, I'm seeing no. This right here, that's all of this. We took x plus h, we substituted it in the place of the x right here. And then we simplified. And then we're subtracting just that original function. So I have minus in my original function. Please, 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 what do I not want you to forget here? Yes, have those parentheses so that you remember to distribute the negative. Super, super important. It will drastically affect your answer. And then over h, because I had it right here. From here, all we need to do now is clean this up. We need to simplify. We need to distribute anything that needs to be distributed. We need to cancel anything that needs to be canceled. So I'm going to distribute that negative. So I have 3x squared plus 6xh plus 3h squared plus 2 minus 3x squared minus 2 all over h. Distributing is done. Time to combine some like terms together, which means we're going to cancel anything that can cancel. What can I get rid of? 3x squared and 2, which means I still have 6xh and 3h squared over h. What do you notice about both pieces up in the numerator? Yes, they have a GCF of h, so we're going to pull that out and cancel it with our denominator. So I have h times 6x plus 3h over h. Cancel these guys out. So fully simplified, this is 6x plus 3h. Good question. Can you take a 3 out as the GCF? Sure, absolutely. You could write this as 3 times 2x plus h. That is equivalent. I would accept that as correct final answer. It's not necessary. I wouldn't count it wrong if you didn't take it out. But it's not wrong if you do take it out. If you are going to take out something more than just that GCF that you're trying to cancel, please make sure that you do it correctly. Because anytime we do extra steps, if you make mistakes there, I have to take off points for any mistakes that are made. Was this a little bit more clear than yesterday? Okay. I want to do another one that is similar to this with one tiny twist. Tell me what my twist is. Yes. Yeah, this one, instead of x, we're going to be substituting in a 2. So I've got 2 plus h, or 2 being substituted in. All right, so let's kind of break it down like we did on the other one. This guy right here. My function rule is this guy, x squared minus 6x. So for f of 2 plus h, I am putting 2 plus h into that function in the place of the x. So I'm going to take 2 plus h and square it, minus 6 times 2 plus h. This is going to go in my numerator. It's going to be the first thing in my numerator. I'm taking this function rule right here, because this is my function f. They want me to substitute 2 plus h in the place of this x right here. So I've done it here, and I've done it here. We need to expand our binomial. We need to distribute that negative 6. What's it going to look like when I expand the binomial? Yes. 4 plus 4h plus h squared. I'm going to distribute this negative 6, so I have minus 12 minus 6h. Can I combine anything? Yes, I can combine my h's together here. I can combine the positive 4 and the negative 12 here. So f of 2 plus h is equal to, I would have, does order matter as I put this back together? I mean, as long as I keep the signs with the correct pieces. So let's see. Yes, ma'am.
So for the f of x, you're using the x squared minus 6x, but then why do you just square 2 plus h?
So what this notation is telling me right here says take this and put it in the place of x anywhere you see x. So in that original function, we had x squared. So I'm going to take what's inside these parentheses right here, 2 plus h, and we're squaring that because that is our input value for x.
Oh, so like just flip it basically, or from what I did, because I was putting x squared minus 6x into the f 2 plus h.
Yeah, opposite direction there.
Okay.
All right, so I've got negative 8 minus 2h plus h squared. Are you guys okay with that? Where are we lost?
So lost.
Where are you lost at?
Because I don't know where my disconnect is. Because where did the x go? The h is at the. Or we just substituted h for x.
Think about what we did a couple days ago. This was last week. Let me pull that out and I will show you. So I'm thinking like Friday last week. Let me pull that up. I'll go back to this in just one moment. So like problems like this. How do you do this? What does that mean?
You're going to substitute all the x's in for -2.
You're going to put -2 in the place of all the x's. That's exactly what we're doing here. We're taking whatever's in these parentheses and we're putting it in the place of every x that we see. In this case, I'm putting 2 plus h in the place of the x's that I see. That's what that notation is telling me to do. It says take what I have inside parentheses and replace the x with that.
Okay. Where did that come from?
It's a difference quotient. This is the kind of output that you will see in calculus. As far as where this fraction came from, that's the problem I'm giving you. That's our starting point. You will never be expected to come up with what's inside these parentheses. You will only ever be expected to take what's inside these parentheses and substitute them in and evaluate it. All right. So this is going to go first in the fraction. So we've got our big long difference quotient here. I have -8 minus 2h plus h squared minus, what do they want back here? F of 2. All right, so let's figure out what f of 2 is. F of 2 means that I need to put 2 in the place of x. So I would have 2 squared, which is 4, minus 6 times 2, which is 12. What is 4 minus 12? -8. This is what I need to go after the subtraction. All over h. And then we're going to simplify it from there. Subtracting a negative, same thing as addition. All right, so I have -8 minus 2h plus h squared plus 8 over h. What can we do? Cancel out our 8's. So I have -2h plus h squared over h. Can I simplify it any more than that? Yes, I can take an h out as the GCF. And then I can cancel my h's. So -2 plus h, fully simplified. Whenever you are given a difference quotient to simplify, they're asking you to substitute in, even if that means you're just leaving it as an x, or in this case they asked us to substitute in a 2. We're going to subtract those 2 pieces, and then we're going to divide by h. And again, I know some of this, you're like, why would I ever even care about doing this? Difference quotients show up a lot in calculus. The calculus part of it is not difficult, but then what do you do with this kind of output? That's why we're practicing this one here. All right, now to that one that was like the homework. I've got these two conditions. What kind of a function are we supposed to write a rule for? Linear. What's the easiest way you know of to write an equation for a linear function? Y equals mx plus b. So the two pieces of information that we need to get from what they gave us is what? If I want to write y equals mx plus b. Yes, we need slope and we need our y-intercept. What is this telling me? Yes, this is our input or our x value. So then what is this then? Yes, this is the output, the y. So they've just given me an ordered pair. They gave it to me in a strange looking way, but they told me the input and the output. So I know that -3, 1 is on this line. So what do I know then from this? Same thing. 3, 2 is on the line. If I have 2 points, is that enough information to find my slope? Yes. How do you find slope again? Yes. Change in y over change in x. y2 minus y1 over x2 minus x1. All right, so I need to subtract my y's. What goes first then?
2.
So 2 minus 1. Careful here. If I put the 2 first in my numerator, what has to go directly below that 2? The 3. The other part of that ordered pair. So this is going to be 3 minus what? -3. All right, so in my numerator, I have 1. What do I have in my denominator? 6. Here's my slope. From here, you can use methods that you learned in previous classes to find b, so you can write it in slope-intercept form. I tend to feel like point-slope form gives me the most straightforward way to substitute in. I know my slope is 1/6. So I have y minus the y part of one of my ordered pairs equals x minus the x part of the same pair. We're only going to use one of these ordered pairs. We're either going to use the green one or the red one. Do you guys have a preference? Green, all right? So it's going to be y minus what? Y minus 2, and then x minus 3. From here, I'm going to distribute to get it into slope-intercept form, so I'm going to distribute my 1/6. What is 3 times 1/6? 1/2. And then I'm going to add 2 to both sides. -1/2 and +2 is going to simplify to what? 1 1/2, or 3/2. Does that help? Okay. Might be very possible. And if it's still wrong when you go back and try it again, let me know. All right. All right.
So could you use point slope form from the original part to find the slope?
Point slope form to find the slope. I would think so, yeah. Because what you would do if you used point slope form is so you had like -3 minus 2 equals m times 1 minus 3, what you would end up doing, because this is going to be your change in y, this is your change in x, and you would have to divide to get the m all by itself. So yes, you could absolutely do that, and that would give you your correct slope. Yep. All right. Time to officially begin 3.5. We've been talking about definition of function up to this point. Every input has how many outputs? One and only one. We're going to talk about graphs of functions. If you have the handout from about a week and a half ago, that's the library of functions, the library of parent functions. It was a paper from the day I was absent with like 9 little graphs on it. This will be very, very helpful today and tomorrow. If you do not have this guy and you want another blank copy, I am happy to provide one. Just let me know. And you can find this, which it was not last Wednesday, but the Wednesday before. The key for this is up in Canvas. Does anybody else want another copy of our Library of Functions handout? All right. First thing we're going to talk about with graphs of functions is even and odd. We've already talked about even and odd, just not necessarily in those words. When we talked about y-axis symmetry is an even function. Y-axis symmetry is the same thing as an even function. So one of the easiest examples of this is a parabola whose vertex is on the y-axis. If I can fold it in half over the y-axis and it matches up with itself, it is an even function. We've already talked about odd functions as well. Odd functions have origin symmetry. A familiar function that you guys probably talked about in Algebra 2 for origin symmetry would be a cubic, whose point of inflection goes right through the origin. Just trying to provide some visuals here. These are not the only kinds, but just kind of what we're talking about. Y-axis symmetry, even functions, this is a type of line symmetry. It's a very specific type of line symmetry. Origin symmetry is point symmetry. So if I had a piece of tracing paper and I were to trace this function on my tracing paper and then put a push pin right on the origin and give it a 180-degree rotation, half a circle, it would line up with itself. That's what origin symmetry is. We had tests previously for y-axis symmetry, x-axis symmetry, and origin symmetry. Do you guys remember doing those? With y-axis symmetry, how do I test for that? Put negative x in the place of x and simplify it. If we get the exact same thing that we started off with, it has y-axis symmetry. We had a test for origin symmetry that was different. We substituted in negative x and negative y and simplified. We can use just a single test. We can use the same test for our y-axis symmetry to test for our odd functions or our origin symmetry. What we would see happen if it is odd, if the function becomes the opposite of itself. So what I mean by that is if you substitute negative x in the place of x, and that is exactly the same as multiplying negative 1 to that original function, then it is odd. So if substituting negative x in the place of x has the same result as if you just distributed a negative 1 to that entire original function, then it is an odd function. If you prefer using the old test for origin symmetry, it will have the same effect. You will be able to identify what you need to. We don't have a special name for x-axis symmetry, because if something has x-axis symmetry, that's indicating it's not a function. For any given input, it would have more than one output. So we don't have a special name for that one, and we're not going to test for that in this part of the chapter, because we're focused specifically on functions here. So I want to test a couple things. If you need to snap a quick picture, go ahead and do that, because I want to put some examples up on the board. Something I want to point out before we do any of our tests, only because this came up several times. This right here is function notation. Function notation means exactly the same thing as what? Y. Same as y. Y is just a generic term that we have for our outputs. We talk about our y-axis. The reason that we have function notation is this right here is the name of my function, and this tells me what I've used as input. Lots of real-world applications for this, especially in computer science, where you have lots of different functions, and you're going to call different variables as inputs for your functions, and so each function needs its own name. That's why we talk about and use function notation. I want to test to know whether this is even, odd, or neither. So we are going to sub in negative x in the place of x. So I have f of negative x. I'm going to substitute that in for x here. So I have negative x to the fourth minus the absolute value, and I've got to substitute it in here as well. Absolute value of negative x. How will this first term simplify? What's going to happen if I take a negative number and I raise it to the fourth power? It's going to come out positive. So that is going to be x to the fourth minus x, absolute value of x. Absolute value of negative x is exactly the same as the absolute value of x. The reason that I can't get rid of that absolute value sign is I don't know exactly what number they're using for x. So if x is a negative number, I can't get rid of it here. What do you notice about this and what we started with? It is the exact same. What does that mean about this then? It is even. Part B, we're going to take negative x and put it in the place of x. If it's even, since we're dealing just with functions, if it's even, it cannot also be odd. When we were just testing for symmetry and we weren't focused on functions, that could happen, but it cannot happen with functions. It's either even, odd, or neither. So we're going to run just one test. Good question. All right, so I put negative x in the place for this x up here. Down in my denominator, I need to substitute negative x in the place of that x. Can I actually do anything to simplify this numerator further? No. What about the denominator? Can I simplify? Yes. When I take a negative number and I square it, it's exactly the same as when I take a positive number and I square it. So this is going to be negative x over x squared plus 1. Are these the same? No. Not the same. So it is not even. Is it the same as if I had multiplied -1 to this original function? Let's look. So negative f of x would be negative, and then my original function x, sorry, I wanted to do that in a different color, x over x squared plus 1. Do these have the same meaning? Yes. Yes, they do. We don't distribute a negative to the top and the bottom, because a negative divided by a negative is a positive. We can take a negative sign that's out in front, we can put it with our numerator, or we can put it with the denominator, but it can't go with both at the same time. So this is the same. My denominators are exactly the same. The numerators are both negative x's here. So what does that mean about this then? It is odd. Part C. I'm going to take negative x, put it in the place of the x. So I would have negative x plus 6. Are these the same? No. So it is not even. Is this the same as if I took the original and multiplied it by -1, distributed -1 to every piece? Let's test and find out. So negative, and I would want to distribute that to x plus 6. That would give me negative x. I like that, but it gives me negative 6, which is not the same. So is this odd? No. If it's not even and it's not odd, I would say this is neither. Last one, part D. We're going to take negative x, put it in the place of x. So I have 2 times negative x cubed minus 6 times negative x. If I take a negative number and I cube it, what's the result? Stays negative. So this would be 2 times negative x cubed. And then I would have plus 6x. So negative 2x cubed plus 6x. Is that what I started with? No. So this is not even. Is this the same as if I distributed a -1 to everything here? Yes. And I'm going to check that just to make sure. So if I had a negative out in front and I distributed that to 2x cubed minus 6x, I would get negative 2x cubed plus 6x. Those are the same. And so that means what? It is odd. Yes, ma'am.
So, but weren't you doing it where it was negative f of x would, and it was like -2 plus 6x, you would, isn't that basically the same thing? Because if you took like a -1 out of that, you'd have f of x equals 2x cubed minus 6x, which is what you started with. It wouldn't that be
But
same?
taking that -1 out, if I could do it to both sides, then yes, if it could cancel with something on the other side. But I have my function notation here. This is just like y. So this is like -y.
So, but then if you divided both sides by -1, then it would just be y equals 2x cubed minus 6x.
Which was our test for origin symmetry previously, where you take a negative, like you sub in -y and -x, and see if you get back what you started with. That was our old test for origin symmetry. This is another way to test for origin symmetry.
But then wouldn't that be same? Because it was the same as when you started. Does that make sense?
Again, if you like, when I just multiply everything here by -1, I do not get the same thing. Even if I factor a -1 out, because then I would have to divide both sides by that, which would undo what I've done over here. When I'm working with function notation, I don't actually have two sides to do things to. All I can do is evaluate one side. So you can factor a GCF out, but that GCF does not go away. And I can't divide both sides by it because, again, when I'm working with function notation, I can only stay on the one side. We don't do operations with this side.
Oh, so but if you had a y.
If we had a y, then we could, yes. We don't typically do operations with our function notation there. But yes, if you replaced it with a y, then you would be running your origin symmetry test that we did before, and then your ideas are absolutely right in line. When you replace y with -y and x with -x, and you evaluate, if you get what you started with, then you have origin symmetry. Yes. All right. Discontinuities. Big word. Horribly large word. Discontinuities are where the graph is not continuous or connected. Discontinuities are where our graph is not continuous, it is not connected to itself. There are three kinds of discontinuities that we are going to talk about in here. The first one is a jump discontinuity. A jump discontinuity indicates that when I am drawing this graph, I would have to pick up my pencil and I would have to move vertically, either up or down, to get to the next place that this graph is. So an example of a jump discontinuity something like this. Right in here, I would have to pick my pencil up and move it to the other dot. That is a jump. One thing I do want to point out about our discontinuities, if this dot is filled in, the other dot cannot be. They can't both be filled in because that would indicate two different outputs for the same input, which would mean it's not a function anymore. It's possible that graphs of things that aren't functions have that, but like I said, we're specifically focused on functions right now. It's possible that neither one of them is filled in. That's okay. That just means it does not have an output. It is undefined for that x value, which is allowed, but we can't have both of them filled in. It's either one filled in and one not, or both of them not. Infinite discontinuities. These are asymptotes. Specifically vertical asymptotes. So a lot of times we won't see these on our graphs. We'll just see the function behavior. I'm drawing one in as a guideline for myself here. So an infinite discontinuity, as we approach this asymptote, it's either going to go up forever or it's going to go down forever. On the other side, we're going to see the same thing happen. As we approach that asymptote, it's either going to go up forever or down forever. They do not have to be going in opposite directions. This is an example of an infinite discontinuity, but so is this. It does not matter if they're going opposite ways or the same direction. They're never going to cross that invisible barrier, and they're never going to connect. And it always heads either up or down as we approach that. Removable discontinuities are holes. So a removable discontinuity could be something like this. So here's my hole. Okay. Real quick, I know we only have about 2 minutes left. Copy this into your notes. I'm going to pass back your quizzes from last week, and this is where we will start tomorrow. I want you guys to have this copied down into your notes so that when you walk into the room, we can start right here. I do not expect you to draw these graphs yet. Were kind of rough.
I don't know what I got yet. Oh my god. Oh my god. What did you do? And you were Naya. You're at like 19 minutes. Really hot. 12 and a half out of 20. I got 8.
You let this like, that's the one I did.
Let me double check if it's going.
I just know how
What do you mean this?
this is a circle. This.
No way I actually got this right.
As long as you signed up on like put your signature in or you added your information, I am not.
So close. I'm so close.
I know there was an initial email that needed to be like correspondence to get the IUIT set up. But that's the only one that I know.
She put her pencil down and she grabbed mine and started using it.
No, you actually did pretty well.